Hello everyone. In this video we're going to go over section 8.2 in area of a surface of revolution. So for a surface of revolution, we pretty much do exactly the same thing that we did with arc length. We first consider a surface that is going to be obtained by rotating a curve y equals f of x around in an interval a to v about the x-axis, and we're going to consider, for the sake of simplicity now, that f is going to be positive and has a continuous derivative. This is going to look something like this. So we have the function, and then we rotate that around the surface of revolution, the axis of revolution, which is the x-axis, and that's going to produce a surface of revolution. Now what happened with this is that we want to approximate what is the surface area of this surface of revolution, and to do that, what we do is we'll start by picking apart a piece, and one piece of this is going to be a cylinder. Since it's a surface of revolution, it's very easy to get just a cylindrical piece that we can use for this. So if we consider a partition of the interval AB with points P0, P1, P2 up to Pi, then we can take a small band or a small cylinder that represents the surface, and for which we're gonna check the surface of that small band. Now remember that we have a division of the interval AB into ends of intervals, and so we're gonna relate each of these points P0 to Pi with the points x0, x1 up to xi. And we want to make the distance between the x a calculation, and so we are going to include equal width between the different points, and so that equal width here is going to be delta x. So similar as we did by arc length, we'll start by approximating the measure. So the measure of that band is going to be like the measure of the surface area of the cylinder. So it's going to be 2 pi r times L. Notice that the 2 pi r is essentially the length of the 2 pi r is the length of the circle, and then we're multiplying by L, which is going to be the length of the band. So of course, if L is the length of the band, we can consider R to be some sort of average between the two different radius that we can obtain for the band. Now, in terms of putting this in terms of the function, then we can see R as 1/2 of yi plus yi minus 1 for the corresponding xi as well. And so in that case, the surface area is going to be just 2 pi, 1/2 of yi plus yi minus 1 times the absolute value of pi minus 1 minus pi. Notice that similar in the calculation to arc length, we get the square root of the distance, and then after setting up the Cartesian distance and considering that this is related to the function and applying the mean value theorem to the function, then we can get that the difference, or the delta yi, is equals to the derivative at certain point xi star times delta of xi. Now if we consider that approximation, then we're going to get to the point where ai is just going to be 2 pi f of xi star times the square root of 1 plus f prime of xi star square times delta x. And so if we again sum over all the partition and take the limit of the sum, so pretty much we make the partition super small, then we're going to achieve converting the sum into an integral. And so the surface area here is going to be given by the integral of a to v of 2 pi f of x times the square root of 1 plus f prime of x squared dx. Now we can also see this in Leibniz notation, and we can change the f prime by dy dx. Okay. Now in terms of what we want for this, remember that we want that f is continuous, and it's going to have a continuous derivative in the interval AB. If we don't have those conditions, then it's kind of difficult to actually consider the surface of revolution, since things might fall apart and might break actually before we even get to rotate around the x-axis. So of course we want f to be continuous and the derivative also to be continuous, so everything is smooth and nice when we're rotating about the x-axis. Now the curves can also be considered in terms of y, and what this means is that we're not going to rotate now around the x-axis, but instead of the y-axis. And so the only change that's going to happen here is that we're going to have a curve that is x in terms of g of y, and now we're going to rotate around the y-axis. So the surface area is going to be given by the integral from c to d, which is going to be the interval in y, 2 pi g of g times 1 plus the square root, times the square root of 1 plus dx dy, since now x is in terms of y. And so this dx dy is going to be square, and then we find all the surface area for this. Now let's see some examples of calculations with this. So initially we want to take y equals 4 minus x squared between the points minus 1 and 1, and find the surface area. Of course we're going to be rotating here with respect to the x-axis, and so this is the integral from minus 1 to 1, and so we have the formula 2 pi f of x times 1 plus y prime square dx. So once that we state the formula, we then are going to replace each of the individual pieces. This is going to be 2 pi 4 minus x squared, and then here times 1 plus, and then now we're going to include y prime, and if the y is this, then y prime is going to be 1 over 2 4 minus x squared, but then multiply by the chain rule is 2x, so the 2 cancels out, and this is just going to be x over square root of 4 minus x squared, and now we get to square everything out. So let's see what happens when we actually compute this. It looks like it's going to be horrible integral, but actually a couple things might actually end up canceling out. Notice that we have here that this becomes 1 plus x squared, and now this is 4 minus x squared. So we can simplify this out. Let's see, minus 1 to 1 to pi square root of 4 minus x squared, and then this is going to be 4 minus x squared plus x squared, everything over 4 minus x squared. This is just by adding 1 plus this in terms of fractions. And now another way that you can see very quickly that this part is this is that 1 can be seen as 4 minus x squared over 4 minus x squared, and so that's why they have the same denominator. Now this becomes 2 pi, and this 4 minus x squared is going to cancel out over this 4 minus x squared that is also going to come up here with a root. So 4 minus x squared, 4 minus x squared, and then you can get to cancel them out. And here I'm only going to get the root of 4 because minus x squared gets to be canceled with that. And so after everything, this becomes a really simple integral. It looks very complicated at the start, but this is just going to be the integral of 4 pi dx. And so this is just 4 pi x between minus 1 and 1. And so plugging in, this is 4 pi minus minus 4 pi x, so plus another 4 pi, and this is going to be 8 pi. So that's the surface area of this particular function. And if you're kind of curious about what that function is, then you can just plug it out just to see what is the surface, what is the area that is being used. So this is like a circle, but because we only considering -1 to 1, then we have the situation. So we only have this arc really here, and so when we're turning around, we get some kind of bend when we make the surface of this particular curve. Now let's go to another example. Now we're going to consider x equals y minus 1 between y equals 1 and y equals 2. So this is a completely, this is now in terms of y. So this means we get to use the formula in terms of y. Notice the formula for this in terms of y is just going to be, of course, the integral from 1 to 2 of 2 pi g of y times 1 plus x prime, x squared, the y. And just replacing what this is 1 over 2 pi, and g of y is going to be y minus 1. And now notice that x prime is what? Well, x prime is actually 1. So it's kind of simple here. It's not going to produce a lot of complications. So we have 2 squared of 2 pi integral from 1 to 2 of y minus 1 the y. So pretty straightforward here. We don't have a lot of things to do. This is y squared over 2 minus y between 1 and 2, and then plug on the different values. When we plug in 2, this is 2 squared, which is 4, divided by 2 is 2, minus 2 is 0, and then minus 2 squared of 2 pi, and then when we plug here, we get 1/2 minus 1. And so this is 0, and this is minus 1/2, and so this is just going to be plus square root of 2 pi. And so that's the final measure for the surface area of this function. Okay, one last example. Let's see what happens with y equals e to the x between 0 and 1. So number 3, y equals e to the x, and we're seeing x between 0 and 1. So we're back here to a function y equals f of x. So the surface area is going to be the integral between 0 and 1, 2 pi f of x, square root of 1 plus y prime squared dx. And so that is 0 to 1, 2 pi e to the x. And so the derivative of e to the x is just e to the x. And so this is just going to be 1 plus e to the 2x dx. This integral can be computed numerically, or whether with a calculator or computer, and you're going to get around 22.93, and so that's going to be the surface area here. Notice that if you're curious about how to calculate this, you can probably transform this to an integral that you can do with trigonometric substitution. So if you do like u equals e to the x, then du is going to be e to the x dx, and so you can transform this one into integral of 0 to 1, or let's forget about the limits of integration by now, and let's say that this is just 2 pi, and then 1 plus square root of 1 plus u squared du. And so at this point you transform this integral to something that you can do with trigonometric substitution. Then at this point you do u equals tangent of theta, And so du is secant square of theta theta. And this is 2 pi, and this is going to give you tangent square plus 1, which is secant, and so secant square. So the square root here is secant again, and by secant squared you're going to get again 2 pi secant cube of theta to theta. This was the integral that I actually made on the first part in arc length, so I don't want to go through it again. If you want to go through it again, then just check it out how you get to the solution with this, and then after you plug in 0 to 1, you're gonna find out that this is 22.83. But I just wanted to show you what was the path for the solution of this type of integral. But the integral is very difficult and is very long to actually finish up. All right, so that's all for the introduction to areas of surface of revolution.